This is a video on solids. We're going to talk about some characteristics of solids. And the first thing we're going to do is realize that solids fall into two general categories, one of which is crystals. Crystals are represented by this repeated hexagon shape shown on the left here. So we'll say crystals are a repeating structure and hexagons is only one possibility. The other type of solid would be called amorphous, which is a type that doesn't have a repeating structure. It is joined kind of randomly in different groupings. So we're going to say not repeating. And a common example of an amorphous solid would be glass. And because of that amorphous structure of glass, it doesn't have a distinctive melting point, which actually allows for some interesting artwork to be done with glass work because it melts over a variety of different temperatures. People often call glass and other amorphous solids liquids, but they're not actually liquids. They are just solids without a distinct structure. A liquid would flow and an amorphous solid does not flow. All right, so we're going to concentrate on crystal structure solids rather than amorphous. And among the crystal type, we're going to consider four different crystal types: ionic, molecular, covalent, and also metallic. And I'm going to talk about metallic first. Okay, metallic is simply a metal. Examples are sodium, iron, aluminum, things that you know to be metals. And they're, as a solid, they're held together by metallic bonds, which we will not go into much detail about. But we do know that they conduct electricity and that they take quite a bit of heat in order to melt most metals. So we're going to say high melting. And that's because they have pretty rigid structures in most cases. All right, then next we're going to talk about ionic. Okay, ionic crystals are things like sodium chloride or magnesium oxide. Okay, all ionic compounds would fall under this category of solid. Ionic crystals are held together by ionic bonds. So when you have a chunk of sodium chloride, you don't just have individual NaCl's separated from each other. It's actually a whole lattice of sodiums alternating with chlorides. And because of the strong lattice that's held with ionic bonds, it is also high melting. All right, and we can contrast that with molecular solids, which includes most molecules like H2, CO2, water, and even bigger things like C2H22O11, which is sucrose or common table sugar. These are not held together by covalent bonds. They are held together by intermolecular forces between the molecules, which is much weaker than a covalent bond. But most molecular substances fall in this category. And because intermolecular forces are quite a bit weaker than ionic bonds, covalent bonds, or metallic bonds, they are relatively low melting. In fact, you may have thought it odd that I included H2 as a molecular solid because at room temperature it is very much not a solid, it's a gas, and the same with water. But they obviously do have a solid form if you cool it down sufficiently. So they melt at a very low temperature, and in fact they melt below room temperature. That's why they are liquids or gases. All right, the final category is the rest of the molecular substances, which are called covalent or network solids. So a few covalently bound species will actually covalently bind to each other. Okay, some few examples of that are solid carbon, also known as graphite or diamond. Okay, those are both just solid carbon held together by molecular bond, or sorry, covalent bonds. Another example is SiO2, which is quartz. And so if you think about graphite, diamond, and quartz, those are all solids at room temperature. They're not held together by intermolecular forces like most molecular substances. They are actually held together with covalent bonds. So we'll write covalent bonds, hold together the solid, and they are high melting. So you can see by looking at these 4 examples that anything held together by stronger bonds like ionic or covalent or metallic will be high melting, whereas things held together by intermolecular forces like hydrogen bonding, dispersion forces, dipole-dipole, those will be low melting because those forces are much weaker. All right, we're going to look at a few more details now regarding how the solids are packed together. So let's look at these pictures. How do atoms, molecules, or ions, depending on which kind of solid it is, pack into a crystal? For simplicity's sake, we're going to look at cubic packing, and we're looking at these 3 examples, which are all in the basic shape of a cube. And if we want to talk about how efficiently they're packed in these cubes, there's 3 different styles here. The first one on the left has balls directly above or next to or behind each other. The next one has some bluish colored ones in between those. So there's the lighter colored ones are spaced a little further apart, and the blue ones are fit in between. And that's actually more efficient packing. Or this style, which has even more of the ones that are in between in a different format. In order to look at how these are actually packed, we're going to take a simple cube out of this bigger cube, and that simple cube is the smallest cube that's a repeating unit. That is known as a unit cell. And so a unit cell is the basic repeating unit in any crystalline solid. So each of these has a different basic unit, and if you look below, we've taken out that one basic unit cell from each of them so we can look at it more closely. All right, and we actually are going to name them or give them a designation, and the first one on the left is the simplest. There's just a cube in each corner of the unit cell, so we're going to call that the simple cubic cell, which we're going to abbreviate as SCC, simple cubic cell. The next one over, if you make the spheres a little smaller, you can see what's going on a little better. So if you down below, we made the spheres smaller. Okay, the blocks in the middle are how they actually pack, but if we shrink the cells or the spheres, you can see how they fit together better. So the next one over shows that it has the same 8 balls in the corners, but then it has 1 in the middle. Okay, and that's going to be referred to as a body-centered cubic, because there's one body in the middle, in the center. Okay, so that is BCC, body-centered cubic. And then the final one has a bluish ball on the face of each side of the cubic unit. There's one on each of the 6 faces. So this is known as a face-centered cubic, which we will call FCC. Now we're going to be able to do some calculations based on these different forms. So we're going to look at some numbers related to them. So I've repeated the picture of the 3 without shrinking the cells. We have SCC, BCC, and FCC. And we can talk about some numbers if we think about how many spheres there are in each cell. Okay, so if we look at the SCC, the first one, we can see that each corner of the cube has 1/8 of a sphere. Okay, if you think about how much more you need to add in order to make it fill up an entire sphere. We have 1/8 of a sphere, and there's 8 different corners, so there's 8 of them. So we have 8 times 1/8. Okay, 8 times 1/8 of a sphere means there's really one total sphere in that unit cell. If you add up all those pieces, you'll get one total sphere. If you look at BCC and look at the light colored spheres, you see you also have 8 there. So we have the same thing plus more. Okay, 8 times 1/8 of a sphere, but there's also a blue sphere in there. And we drew them different colors only so you can see them. They're all the same size. So it's one more, which means the BCC has 2 total sphere volumes in its unit cell. And if you look at the FCC, face-centered, again, you have the 8 1/8 pieces in the corners. And then you also have a half a sphere on each face. See, that's a half a sphere on each face, and there's 6 faces. So you have 6 times a half a sphere. So that's a total of 4 spheres in that unit cell. And that is actually the most tightly you can pack them into a unit cell, that way of doing it, the FCC. So we call this a closest packed solid. Now we can do calculations comparing the length of one edge. Okay, what's the length of one edge? If we look at the SCC, we can call that length A, and that's just the length of one side of the unit cell. And they're all the same because it's a cube. Okay, all sides are the same. So that's A. It's also known as the lattice constant. So that's the size of one unit cell, or the edge length of one unit cell. And then we can compare that to the spheres, because remember the spheres are atoms or ions. And we can compare that to the sphere where the radius of the sphere is simply the radius. And on this one I've drawn it on, it's actually the whole length shown there, because that's one radius is shown in length. All right, so we're going to do equations that compare the edge length A with the radius of each sphere in the solid. All right, so it's fairly easy for the SCC to see that since the spheres touch each other in the middle, that A has 2 radiuses in it. So the one for SCC is actually really easy to write. We say that A, the edge length, equals 2 times R, whatever the radius of the species in the unit cell. I'm going to jump over to the FCC next, which is the next easiest one to do. And we're going to look at the fact that there is a diagonal here, which we're going to call C, because we can use Pythagorean's theorem, and we can see that the other 2 sides of that right triangle are actually both A. Okay, they're both the edge length. So we can use Pythagorean's theorem, but the first thing we can see is that C has a radius here from one sphere, 2 radiuses here from the middle blue sphere, and then another radius here. So C is equal to 4R. And then since we use Pythagorean's theorem, C squared equals A squared plus B squared, but A squared and B squared are the same in this example, so we can say it equals A squared plus A squared, which means it's 2A squared. All right, then we can substitute in the 4R for C, and then we can solve for A. So we get, the result is A is going to equal R times the square root of 8. And that is how R and A are related for FCC. Finally, we'll do BCC, which is the most complicated. In this case, our hypotenuse is going to be actually diagonal in the cell, all the way from one corner to the far corner, rather than just along one face, as it was in FCC. So in this case, our C is a different C, But you can see that that C is also 4r. There's a radius here, there's a radius here, and then there's a blue one in between. So we can still say, for this case, C equals 4r. And now we have to label we have an A along this dimension, but our B is not the same as A. It goes diagonally across the cell. All right, and then B is also a hypotenuse for a different triangle, so it gets complicated. All right, so let's first write C squared equals A squared plus B squared, but then realize that B is also the hypotenuse of a right triangle, okay, which is just like it was for the FCC case. B squared is now equal to A squared plus A squared, or 2A squared. So we can substitute that in for B squared in our original equation, and we get C squared equals A squared plus 2A squared. Okay, so we use this equation, substituting in 2A squared for B squared. All right, then let's put in our value for C, which is 4r, and C is squared, and then A squared plus 2A squared is 3A squared, and then we can solve for A. We get A equals 4r over the square root of 3. So these are, for each of these three types of solids, these are the equations which relate edge length to the radius of the spheres. Remember, the spheres are either an atom or an ion in the solid. All right, so what is the point of this? I'm going to show you some examples of a few things you can do with this information. I'll give you two examples of unit cell calculations that you can do. All right, so the first one. Tungsten crystallizes into a BCC unit cell with a lattice constant, or edge length, of 317 picometers. What's the radius of an atom of tungsten? So we look at the BCC unit cell from the previous page, and we see that the edge length is equal to 4r over the square root of 3 for a BCC solid. Okay, we want to know r. Okay, the question is asking us for the radius, so we'll solve for r. R will equal square root of 3a over 4. And so we can substitute in our value for A, 317 picometers. Doing the math, you'll get R equals 137 picometers. Okay, I just made it a little bit bigger, but basically if you're given the lattice constant or edge length, you can calculate radius for any solid, or if you're given the radius, you can calculate the edge length for a unit cell. But there are some even more interesting types of calculations you can do, which involve density of a solid. So let's do an example of that. This example tells us that nickel has an FCC unit cell, face-centered, with an edge length of 352 picometers. What is the density of nickel in grams per cubic centimeter? So we just have to know how big a unit cell is to figure out its density. All right, so let's think about this. Density is mass divided by volume. And so we're going to use the volume of one unit cell to do this calculation. So that will be our volume. And first we'll do the mass, and then we'll do the volume, then we'll divide. So the mass, we need to know the mass of nickel that's in one unit cell. Well, we certainly know the mass of 1 mole of nickel cells. We can get that from the periodic table. 58.6934 grams of nickel per mole. Okay, we definitely don't have a mole of nickel in one unit cell though. But we can figure out the mass of 1 atom of nickel by dividing by Avogadro's number. All right, and then we use the information that we got earlier that tells us how many atoms of nickel are in a unit cell. So we go back up here, and we can see that in one FCC unit cell, we have 4 atoms in a unit cell. Okay, since nickel uses FCC, then we can say that nickel has 4 atoms of nickel per cell. Okay, so we first figure out the mass of 1 atom of nickel, then we said there's 4 per cell. All right, so what is that? So this is mass of 1 atom times 4. All right, so that number ends up being 3.8986 times 10 to the minus 22 grams per cell, per unit cell. That's the mass. How about the volume? Okay, well, we're given the edge length, and since the edge length times cubed is the volume of a cubic cell, we can simply cube it, except for one problem, and that is that we want our density in centimeters cubed, not picometers cubed. So let's first write it as 352 times 10 to the minus 12 meters, and that's per cell. And we're going to cube it because we need the length cubed to get the volume of the cell. But then we're going to put in the conversion factor that there's 100 centimeters per 1 meter, and we have to cube that conversion factor. All right, so then we do the math. We get 4.361 times 10 to the minus 23rd cubic centimeters per cell. Finally, we just divide. The density is the mass, 3.8986 times 10 to the minus 22 grams per cell, divided by the volume, 4.361 times 10 to the minus 23 cubic centimeters per cell. Okay, the per cells will cancel, and you get 8.94 grams per cubic centimeter for nickel. So in addition, you could be given the density and figure out the edge length or the radius if you're given the right information about what type of unit cell it is. Finally, I just want to point out that the cubic unit cell, which is what we've been doing, we showed 3 types of cubic, but cubic is only one of 7 different types of shapes that we can have for solids. Okay, so we've been looking at only cubic, where the 3 lengths, the length, the width, and the height are all identical. There are several other different forms that solids can take, and the calculations would be different for all of those.